talks, and the next speaker, I am sure, is known for most of us as one of the strongest researchers in the intersection of algebraic combinatorics and permutation group theory. And it is my pleasure to ask him to give a talk about generalized dihedral CI groups. Please.
Yeah, thank you, Ilya, for strong compliments. So I'd like to also thank the organizers who invited me again to Akademgorodok. So I will talk about CI problem, or Keller isomorphism problem, and the title is Generalized Dihedral CI Groups, and this is joint work with Ted Dobson and Pablo Spiga. So I will start with a definition of a Keller graph. Of course, everybody knows what is a Keller graph, but let me remind, I take a finite group, I take a subset of a finite group, and then I define a graph connecting two vertices if they satisfy this inclusion. So the Keller graph is connected if the connection set, this set S is called the connection set. So it's connected if the connection set generates a group. It's undirected if the set is symmetric. It has no loops if the set does not contain the identity. And what is important, the automorphism group of the Keller graph contains a regular permutation subgroup, which is isomorphic to H. Namely, this subgroup consists of the right translations by the elements of H. You know, the problem I'm going to talk about is isomorphism problem for Keller graphs. So given two Keller digraphs, I want to decide whether they are isomorphic or not. And this is a particular case of the famous graph isomorphism problem. And although we know that there is a great progress towards a solution of graph isomorphism problem, but we still don't know whether the general graph isomorphism problem has a polynomial solution. But together with the general problem, for which we cannot find an efficient solution, we can look for special classes of graphs and hoping that for this particular class of graphs, we can find a polynomial solution for the isomorphism problem. So many such classes of graphs are known. For example, the class of trees and planar graphs, etc. But the Keller graphs is a unique case where you have highly symmetric graphs. So the question is, if I know that my two Keller graphs share the same, share some groups of common automorphisms, does it help to recognize their isomorphism? Now, for Keller graphs, there is a natural definition which is called a Keller isomorphism. So if I take an automorphism of my group and apply it to Keller graph, then I certainly will have the Keller graph over the same group, which is isomorphic to the original one. So this leads us to the definition that two Keller graphs are Keller isomorphic if and only if there exists a group automorphism which maps one to another one, or it's equivalently that there is an automorphism which maps one connection set to another connection set. So, and Babai in 1976 introduced Kähler isomorphism property for Kähler graphs. Actually, he introduced this property not only for graphs, but for general Kähler combinatorial objects. But main part of my talk, I will talk about the graphs. So he defined a Kähler graph have Kähler isomorphism property, CI property for short, if any other Kähler graph over the same group is isomorphic to a given one, if and only if it is a Kähler isomorphic. And the group is called DCI group if every subset has that property. It is called CI group if every symmetric subset satisfies CI property. That means a CI group has Kähler isomorphic property only for undirected graphs. And we say that H is a CI2 groups, meaning that it has Kähler isomorphism property for colored Kähler digraphs. So I'm not going to define this explicitly, but it's clearly that CI2 property is the strongest one, and we have this implication here, right? But the converse implication does not hold in general. And the following problem was formulated by Baba and Frankel 45 years ago. Which groups are CI groups? And although the problem was formulated in 76, but actually the first shot in the area of isomorphism problem for Kähler graphs was done 10 years later by Andras Adam, who formulated this conjecture in 67. So using the notion of CI group, we can formulate this conjecture as follows. The cyclic group of order n has Kähler isomorphism property for every n. Of course, the original Adam conjecture was not formulated in these terms, but it's equivalent one. Now, very soon it was realized that is not true. So the counterexamples were found by the people you see here. And it was proven that Adam's conjecture is not true for directed graphs if n is divisible by 8 or by a naught square. So for undirected graphs, there are more values of n for which Adam's conjecture is true. Now, of course, this theorem shows that Adam's conjecture fails in general, but there were found infinite series of orders for which Adam's conjecture is true. And you can see the names, and I want to point out two papers. The one is the paper of Babaim, this one. So, and in his paper, he showed that this problem, CI problem, or problem how to determine whether your graph is has a CI property, is actually a group theoretical problem. So you have to take the automorphism group of a graph and to look at the conjugacy classes of regular subgroups there. So the answer is hidden in the automorphism group of your graph. And the second paper I want to mention is a paper of Klein and Pirschen, where they proposed the first time to use Schuring in order to attack isomorphism problem for circular graphs. And this approach turned out to be very, very fruitful. A lot of results in this area were obtained later by this approach. Now, since every talk should have at least one proof, I want to show you 2 examples. So I take a group Z8, the cyclic group of order 8, and I take 2 Kelly graphs, Kelly digraphs over this group. You can easily check that they are not Kelly isomorphic because you have only 4 automorphisms of the group Z8, and none of them maps the first connection set to another one, but they are isomorphic, and the isomorphism is given by this permutation. So if you exchange the point 2 and 6 for 7 and doesn't move the others, it will be isomorphism. So that means that Z8 is not CI group with respect to directed Kelly graphs, but it is a CI group with respect to undirected Kelly graphs. So let me give you the short proof of that. So we take an undirected Kelly graph, so 2 of them, gamma and gamma prime. So if they are isomorphic, they should have the same cardinalities of connection set. And because the graphs are undirected, so the connection sets should be the unions of some sets from here. Now, because the graphs are isomorphic if and only if their complements are isomorphic, so I may assume that the connection sets have cardinality at most 3. So if both graphs are connected, then it leaves us 2 choices. Either the connection set has cardinality 2 and coincide with either S1 or S3. And in that case, the graphs are just 8 cycles, and they are Kelly isomorphic. You can apply multiplication by 3 and move one connection set to another. The second case is when they are cubic graph, and this is possible only if you add this set to the connection set, and also in this case you can check that they are Kelly isomorphic. If gamma is disconnected, then you cannot take S1 or S3 into the connection sets. You are left with S2 and S4, and then just by comparing the cardinality, you can say that the graphs are Kelly isomorphic. So this shows that Z8 is a CI group with respect to undirected graph, and the corollary we have that CI property does not imply the DCI property. Now, as I mentioned, that there are 45 years since the problem was formulated by Babe and Frankel. So, and during these years, a lot of people involved into the solution of this problem. I gave the list of names, not in the alphabetical or chronological order. There's just the names that are mentioned in our paper, right? So we have some conditions which gives us the necessary conditions, and we these necessary conditions give us certain class of groups, but the sufficient conditions we have they give us only a subset from this necessary class. So we still have a gap between necessary and sufficient condition. So let me formulate what was known before our result. So necessary condition for being CI group is this. So you take the group H, and if it has an element of order 9, right, then the list of the candidates into being CI groups is very short, right? There's only 7 groups here, as you can see. Now, if the group H has element of order 8, then the group should be isomorphic to this one, or Z8, but actually Z8 is a particular case of the group EM8, and I will define this group a little bit later. So, and if H has no element of order 8 or 9, then it should be a co-prime direct product of the groups from the following list. So elementary abelian group, the rank of which is bounded by this number, Z4, or this non-abelian group, which you can see here. And what is EM2, 3, 4? So M here is a direct product of elementary abelian groups. And EMN is semi-direct product of the group M by an element Y of order N, which acts in the following way. If N is 2, 4, or 8, then Y inverts the elements. But if order is 3, then this semi-direct product is a special type of Frobenius group. And I'm not going to detailize what Frobenius group is this, because I want to move to necessary conditions for DCI groups, where this Frobenius group does not is not included. So if I write necessary conditions only for directed case, then we have still this elementary abelian of Z-bounded rank, Z4, and these groups, non-abelian. Now, the groups EM2, it is what is called generalized dihedral group. So it's a semi-direct product, as I told before, by an element Y, which acts by inverting the elements of M. Now, these are necessary conditions. So the list of group is short, but one of the problems is that you can take a co-prime direct product of groups from this list. And that means you can get more groups than are mentioned in this list. So what about sufficient conditions? For sufficient conditions, if I look for abelian groups that you see here, right, that you see here, then we have the following result. So we know that Z4 is a DCI group, and that's actually a quite easy result. For elementary abelian group, we know that all elementary abelian group of rank at most 5 are DCI group, yeah? So, but on the other hand, we know that the bound is 2p plus 3, so it's quite far from 5. Now, for elementary abelian group of characteristic 2, we have a complete answer. Elementary abelian group of exponent 2 is DCI if and only if its rank is less or equal than 5. Now, for characteristic 3, elementary abelian group of characteristic 3, we know that Z3 to the 5 and less rank is DCI. And we know, due to Pablo's figure, that Z3 to the 8 is not DCI. And for these two values, we don't know. Now, in general, there is the following problem. I give you a prime number and I want to know what is the minimal rank such that the group is not DCI. So due to Gabar-Somley, we know that this rank is at most 2p plus 3. But we don't know exactly what it should be. So among non-abelian group, what was known is that, sufficient condition, one can check these small groups, they are DCI groups. And we know that the dihedral group of order 2n and its central extension, which is called a decycling group. So a decycling group of order 4n are DCI groups in the case when n and phi of n are coprime. So this is what we know for the groups in the list. But now remember that we can take a direct product of the group from the list when the groups are coprime. So when coprime direct product gives us a CI group, a DCI group. So with Istvan Kovac, we made a conjecture that if I take two DCI groups and they have coprime orders, then their direct product is a DCI group again. And since then, we have a number of results which support this conjecture. So we know if both groups are cyclic, it's correct. If one of them is cyclic of prime order, the other one is elementary abelian of rank at most 4. We know that if one of them is ZP to the square and the other one is cyclic of square free order. So, and for all these values, we have results that support the, so we have no counterexamples to that. But surprisingly, for CI groups, the conjecture is not true. The counterexamples, actually an infinite series of counterexamples was found by Ted Dobson recently. So, but we cannot use this series of counterexamples to get a counterexample to our conjecture. So it's still open. So these are two main open problems in CI. If we can answer these two problems, then we can somehow close the question. And now I'm going to present my result, the main result of my talk, which is a joint result with Ted Dobson and Pablo Spiga. So you remember that we have this group EMN, where in the case of n is equal to, it is just generalized dihedral group. For n is equal 4 and 8, this is a central extension. So, and so we prove that if it is a CI group, then for every prime divisor of order of m, a seal of P subgroup should have order P. Or there is one exception. If P is equal 3, it could be 9. Now, if this group has a DCI property, so for directing graph, then n cannot be 8, and the seal of 3 subgroup should be of order 3. So for DCI groups, we have, in this case, that M should be a cyclic group of odd square free order. So now the outline of the proof. So Babay and Frankel, they proved that the subgroup of CI group should be a CI subgroup. And Dobson and Morris quite recently proved that the quotient of a CI group should be a CI group. So now if I take my group EM2, then I know that if P squared divides the order, then it should contain this as a subgroup. So our goal was to show that this is not a CI group if the rank is more than 1. So, and this is the main result. It says if I take a not prime, and if I take the generalized dihedral group over elementary abelian group of rank R, then rank should be 1 if P greater than 3, and maybe 1 or 2 if P is equal to 3. And if I look also for directed graphs, then the only possibility is rank 1 here. So that means for directed graphs, this group should be just the dihedral group of order 2 times odd square free number. Now, and there is an old result of Babay which says that if I take my rank to be 1, then it is a CI group, not only with respect to undirected graphs, but also to colored kilographs. So certainly, in certain sense, we do know what non-commutative groups from this list should be a CI group. But still there is one question which remains open. And this is, if I take a dihedral group of order 2 times a odd square free number, is it true that this is a DCI group? So if we answer this question, then we somehow could close the problem for non-commutative groups. Now, how to check a CI property for a given group H? Now, the basic fact is the automorphism group of Kelly graph. It contains a subgroup of which is regular and isomorphic to H. And Babay proved the theorem that the Kelly graph has a CI property if and only if every subgroup which is regular and isomorphic to H, I mean the subgroup of the automorphism group, which is regular and isomorphic to H, it should be conjugate to this regular subgroup HR. So now if you want to apply this result, you can take all possible Kelly graphs, compute the automorphism groups, and then check that all H regular subgroups are conjugate. If they are, then the group has CI property. If there is someone which have more than one conjugacy class, then it's not, and you have a counterexample. But of course, there are too many Kelly graphs, and you can do a better search if you look for the automorphism groups of Kelly graphs, because different Kelly graphs may have the same automorphism group. For example, if you take the circular graphs, the Kelly graphs over the cyclic group ZP, where P is a prime, you have almost 2 to the P Kelly graphs, but the number of automorphism group is less than P. So the number of automorphism groups is quite small. Now, not every overgroup of this regular subgroup will be the automorphism group of certain graph. So we have to take this regular group, and then we have to find two closed overgroups, all two closed overgroups, and look inside each of them whether H regular subgroups are conjugate or not. Now, well, it's not a good algorithm, right? But that's one of the methods that we know. And I'm not going to tell about the usage of Turing's in this approach. So now I'm starting to describe an example. So I have to show you that the generalized dihedral group, for ZP square has a connection set whose automorphism group contains two non-conjugate copies of the regular subgroups. And now let me describe the situation. So I start with a group G, which is upper triangular matrices, but on the diagonal, you take only plus minus ones, and the determinant should be equal to 1. So the group has order 4 times P cube. Now inside, you take a subgroup, we denote it as D. This is a subgroup. It has order 2 times P. And actually, it's isomorphic to the dihedral group of order 2P. And then we take 2 additional subgroups, H and K. So you can easily see that H and K are isomorphic. And these 2 subgroups, H and K, they are isomorphic to the generalized dihedral group over ZP square. Now we take the group A, G, and consider the action on the right cosets over the group D. So one can check that this action is faithful. So just because the subgroup D does not contain any normal subgroup of G. So, okay, we have an action which is faithful. Now, in this action, we have regular subgroups. Now, the groups H and K that I mentioned before, they are isomorphic to generalized dihedral group over the ZP square. They are normal subgroup in G, so they are not conjugated in G. They intersect D trivially, and their product with D is equal to G. So that means that H and K are regular subgroup in the action of G on the set omega. So we can identify omega with H via this map. Well, you remember that omega is the set of the cosets. So every coset of D can be uniquely represented in this form where H is taken from H. So and if I take this under identification, I may consider now that G acts on H. G acts on H. Now let me abbreviate the element of H in this way, and elements of D in this way. Now D is now a point stabilizer. So I take the identity of H, and the action is like that. If I take an element from group H and consider its action on an element of group H, this is just a product. And this is a product in a semi-direct product in a generalized dihedral group. So the second type of action is I take an element from group D, the point stabilizer, and it is an automorphism of generalized dihedral group, which acts in this way. So that's just a formula. And if I take the orbit of the point stabilizer, which is a D, and this is a point stabilizer of the identity, so I get three types of orbits. So singletons, the orbits consisting of one element, pair of horizontal lines, and parabolas. So, and every two orbits of my group G acting on H is a Kelly graph of that type, where S is one of these D orbits. Let me show you the picture which shows these orbits. So the generalized dihedral group, it has a normal subgroup of index 2. This is a one plane. And the complement is somehow another plane. So here we have on the axis, on the x-axis, we have singleton orbits. And outside of that, we have orbits. Each orbit is a pair of parallel lines. And on the complement, the orbits are parabols. If you look at the equation, the geometrical, these are parabols, and these are the suborbits. Now, so first we show that the action of G on H is too close. How we do that? We say, let's take this suborbit, the orbit of a point stabilizer. And we show that if I take the point stabilizer of two closure, then it should act faithfully on this parabola. And the second thing, if I take my two orbits of my action and restrict it to that parabola, I will get very nice graphs. So my graphs will be just p cycles. So, and the automorphism group of a p cycle, it should be the dihedral one. And we know that the original group, if I restrict the action of point stabilizer on the parabola, I will get the dihedral group. So this is how we prove this is too closed. So because this is too closed group and it contains two regular subgroups which are not conjugate, I can tell that H does not have CI property for colored Kelly digraphs. But now I want to build just one undirected graphs which has the same automorphism group. So it wasn't easy. It took a bunch of computer calculations, so roughly speaking, we took three parabolas and and one pair of lines and two singletons in order to get a connection set, the automorphism group of which generate is the same as G. And in order to prove that the group, the automorphism group is the same as G, we use calculations in the shoe rings. So we are lucky to get such a set only when P is not equal to 3. For P equals 3, there are no symmetric set, generating set, which have the same automorphism group. So that means that any symmetric subset of this generalized dihedral group has CI property, but it does not have directed CI property. I can find a non-symmetric connection set for which the automorphism group will be equal to G. Now, that's what we have done. And now the project we are working now is related to CI property for K-area relational structures. So what is relational Kelly structure? So you take a bunch of relations of differentiarities on set H, and this tuple is called relational Kelly structure if every relation is invariant under the group HR. And the arity of this tuple is the maximal arity of the relations. And a group has a CI property with respect to K relational structures if and only if two H invariant structures are isomorphic, if and only if they are Kelly isomorphic. And actually this was the relational Kelly structures, and their Kelly isomorphism was introduced by Babai in 76. So one can show that if group has Kelly isomorphism property for structures of arity K plus 1, that then it has it also for arity K. And the Palfy theorem, Palfy in 87 proves that a group H has a Kelly isomorphism property for all possible relational structures, of course, invariant under the action of H, if and only if the group H is one of those. And so for that group, you can take an arbitrary combinatorial object you like, for example, Steiner system or codes or something else, and these two combinatorial structures will be isomorphic if and only if they are isomorphic by an automorphism. Now, he also proved that the groups that you see here are the only groups which have CI4 property. So that means if I take a group which is different from those in the list, they don't have Kelly isomorphism property for quaternary structures. So actually, the CI property is open for ternary relational structures and binary relational structures, So for binary relational structures, we are working with graphs, and for ternary relational structures, this quite fresh area of research, which was started by Ted Dobson, and now we continue with Ted and Pavla working on this problem, whether is it possible to classify these CI3 groups. How much time do I have?
You have 7 minutes.
Okay, great. Now I can come back to the cyclic group, to kilographs. Sorry. So we can formulate the isomorphism problem for kilographs in the following way. Does there exist an algorithm which solves the isomorphism problem for kilographs in a polynomial time, right? And but it's not an easy problem, because if there is such an algorithm, it will solve an isomorphism problem for finite groups in polynomial time. And we know that this is an open question. So we can take a more modest problem. We can take a class of finite groups and hope to build an algorithm which solves an isomorphism problem for Z graphs in a polynomial time. So if I know that my group is CI, then an isomorphism problem is easy. I have to check all the automorphisms. And if my group don't have many automorphisms, which happens, then I have, well, if the number of automorphisms is polynomial, then I would have a polynomial automorphism, a polynomial algorithm for isomorphism testing for CI groups. But if the group is not CI, so can I still do it polynomially? So let us come back to the circulant graphs. And for circulant graphs, there are two results. So the first, it's my old result, which says if I take a cyclic group, then I can write down a set of permutations of polynomial size bounded by n cube, such that any two kilographs are isomorphic. If and only if you can find a permutation in this set which maps one graph to another. So this gives us a polynomial algorithm. Another approach was proposed by Yevdokimov and Ponomarenko. So one can easily prove that if I take two circulants and they are isomorphic, if and only if the disjoint union is a circulant graph. So you have to take the disjoint union and to check whether it is a circulant graph. And this algorithm was built by Yevdokimov and Ponomarenko. There is a polynomial algorithm which decides whether a given graph is circulant or not. Now, if I switch from graphs to arbitrary circulant or cyclic combinatorial objects, so there is an algorithm which check an isomorphism of two circulant or cyclic combinatorial object of size n. Well, size of the object is so to speak, the size of input you need in order to write down your objects. So for example, for Steiner triple system, the size of the objects is the number of triples, so to speak, not the number of points. So anyway, if you take two cyclic objects of size n, so one can test in a polynomial time whether they are isomorphic. And the polynomial is not in the number of points, but in the size of object, which can be much bigger than the number of points. And I want to finish my talk with a result which says that actually Adam's conjecture is true, but not for graphs, but for a special class of combinatorial structures. If I take a cyclic group and consider symmetric balanced configuration. So a balanced configuration is a regular hypergraph where the number of hyperedges is the same as the number of points, and every point is incident to the same number of hyperedges. Every hyperedge contains the same number of points. Every 2 points are contained in at most one hyperedge, and every 2 hyperedges intersect in at most 1 point. So if we take those combinatorial structures, and they do exist, it's not an empty set, then for these structures, the Adams conjecture is true as it was conjectured by Adam. So thank you for your patience.
Thank you, Misha. And are there any questions? Maybe comments, remarks? At least I have one. You see, you always speak about a problem for graphs, for Kelly graphs, and this means that we always speak about regular subgroups. But if we change our setting and consider not a graph admitting a regular subgroup, but a graph admitting a transitive group, can we say something about this kind of results?
Well, if your subgroup is transitive, then certainly, but not regular, right? So you
Yes.
have more than n permutation. So the bigger group is, the easier problem is. Okay, so if you take a transitive group, which is not regular, for example, take the dihedral group, right, instead of cyclic, then it will be easier than the general case, right? And well, I want to say that Reinhard Laue considered an isomorphism problem for general combinatorial structures which are invariant under a given, not necessarily transitive, but any subgroup of permutation groups, and he developed an enumerating algorithm how to find, for example, codes which are invariant on these subgroups, and how to find which of them are equivalent or non-equivalent. So, but in general, the problem was not considered if the group is not regular, right?
Okay, thank you.
One small question, please.
Of course. Please.
To Misha and to Ilya, what is a circulant object in your joint theory? Circulant object, please explain.
Okay, this is, so think about any bunch of relations, any arity, binary, ternary, whatever, defined on the cyclic group Zn, and each of those relations should be invariant under the cyclic shift. So this is a circulant object.
So no special, no transitive action.
No. The action is transitive on the points, but it's not transitive on each relation. No.
Important.
For example, if you take, for example, Kelly map, you may consider Kelly map as a special ternary relational structure. which is invariant under the regular group.
Yeah, maybe another kind of questions. Bicirculant graphs or just action circulant groups with a finite number of orbits. Is it suitable for your theorem or not?
Well, it is not, but there are some papers which studied bicirculant graphs or multi-circulant graph. There is a paper of Istvan Kovac, Dragan Marušić, and other authors.
Yes, I know.
Yeah, which is dedicated to that. But the isomorphism problem, well, it was studied for bicirculant graphs by Istvan and his PhD students, and there are some results. But this problem was not studied much. Yeah.
Okay, thank you very much. Okay.
Thank you for the question.
An important remark that when we speak about combinatorial object, then all the set of relation is linear ordered. You see, so the automorphism cannot permute these relations. This is important thing.
Okay.
Okay, some other questions, comments? Good. Thank you, Misha, very much for your talk.
Thank
Okay.
you.